All right, good morning and welcome. So again, the lecture is being recorded. So we'll continue our discussion of the Fourier transform. So last time we talked about the definition of Fourier transform. For FT. So we have a signal. This is a waveform that is falling under the category of signals that are Fourier transformable. So this is a finite energy signal. Generally speaking, it is complex value, but it doesn't have to be. It could be real too. And if you take such a signal, you can define this mathematical operation, complex function capital X as a frequency of f. So this is my frequency variable. Right, and f is real value. But x of f is in general complex value. This is defined by definition as the integral of negative infinity x of t e to the minus j 2 pi t t, where j is by definition root of So the Fourier transform satisfies a number of mathematical properties, which we will systematically cover in the course. Today, we will talk about the simplest of these properties, the linear time invariance properties. So I'll give you a minute to make a note and then we'll move forward. So let's look at some properties. All right, so one, linearity. So we have x of t and its corresponding Fourier transform x of f. So this symbol is called the Fourier transform pair, the double arrow, right? Small x of t has a capital X of f Fourier transform, and capital X of f has a inverse Fourier transform small x of t. So this is a two-way operation. If you have small x of t, you can find capital X of f, or if you are given capital X of f, there is an inverse operation which we will talk about how to get back into x of t. So if you know one, you can calculate the other, right? So the linearity property basically says that if x of t has a Fourier transform x of f, if I scale x of t by a constant alpha, right, so t, then the corresponding Fourier transform is simply of f. Scale 1, the other one is similarly scaled. So it's easy to prove, right? We can start by the definition. X of f defined as so let's call the Fourier transform of alpha times x of t. So this is small x. Let's call the Fourier transform of this whole thing x prime of f or x1 of f. So x1 of f defined as the Fourier transform. Putting alpha here, alpha. So alpha is a constant, so the constant pops out. Comes out. So I can write the answer as alpha times right, and this is basically so my final answer is simply alpha times x of f. Very trivial, easy proof. So the take-home message is that if you have a Fourier transform capital X of f for small x of t, if I scale x of t by a constant, a small constant, that small or large, it doesn't really matter, any constant, that constant similarly scales the frequency domain. So I should say that alpha is a constant. And typically alpha can be complex variable. All right, so let's move on. To delay property. If small x of t has a capital X of f Fourier transform, we can show that the Fourier transform of x t minus tau is capital X of f e to the minus j 2 pi f. So if you have a Fourier transform x of f, capital X of f of small x of t, right? I delay the time domain by some delayed tau, right? So this is my delay. This is my delay. And the fact that we are delaying the signal in time domain causes a phase rotation in the frequency domain. So this is the original spectrum. This is my Fourier transform of x of t, of x of t, and this part is a phase rotation. Yes, Daniel.
minus tau.
Yeah.
Wouldn't it make more sense if you were to do the tau on the other side something different, because it wouldn't be exactly the same tau as tau?
It's just a constant. So you can call it whatever you like. You can call it T if you want. But don't be stuck on a single letter. Right? It's just variable. All right, so let's see how we can do that. So we have, let's call the Fourier transform of this one, right? Xt minus tau is the derived version. Let's call it x1 of f. So by definition, x1 of f is given as the integral xt minus tau minus j 2 pi ft. That's by definition. So what I'm going to do is, I'm going to do a temporary variable. I'm going to define, let's say t dash is equal to t minus tau, which means that t is equal to t dash plus take the differentials, dt is equal to dt dash plus d tau, but this is a constant. Because it's a constant, the d tau component is 0. So dt, I can plug into the equation, I get x1 of f is equal to x tau dash to the j pi ft is plus tau so I'm going to come over here. I think we can still see it. I can see that there is a 2 pi f t dash plus tau component. I'm going to write it as the product of two exponentials. Right. So I'm going to write this equation as x1 of f is equal to xt dash e to the minus j 2 pi f t dash times e to the minus f tau the only thing I did was I took the complex exponential component, which has a plus sign here. So in the exponent, if I have a plus sign, I can write it as the multiplication of two exponentials, right? So I'm using the fact that e to the x plus y is equal to e to the x. Right. But notice that in this expression, the independent variable is now t dash, t dash, t dash, t dash. That's the variable. The tau component is just sticking there, but it's a constant as far as t dash is concerned. So it's like you have a constant here which can pop out. So I can pop that out from this integral. It comes out because it's not a function of t dash. So I get it out e to the j 2 pi t dash here. Then I get the rest of the integral. T dash j 2 pi t dash. This is by definition. Think of this as a dummy variable. This is by definition x of f, because the limits go from infinity to infinity, right? So whether it's t dash or t, it doesn't matter. It goes all the way out to infinity. So this is the x1f that we are looking for. Is equal to x of f minus j. So I can write this part as an angle theta. So x of f. Yes.
Did you change you took the constant out? I understand that, but why did you change it to tau prime? Isn't it just regular tau?
Yeah. Done. Good. Not enough coffee. So this is a phase rotation. So the reason I called it a phase rotation is that if I take a moment to look at this function, okay, let me erase it so that we have space. Would you mind? Space. All right, I'm going to erase this. And we'll talk about this phase rotation. All right. So we said that if x of t is the time function and you compute its Fourier transform, it has x of f, which is a complex function, right? So it's a complex valued function. Then the delayed version, xt minus tau, has a Fourier transform. X of f, unchanged, the same one, but it's got an extra term, e to the minus j 2 pi f tau, where I call this component 2 pi f tau delta. So I can write it as x of f e to the minus j delta. And I'm calling this theta a phase rotation. Why is it a phase rotation? So let's look at this function separately. If I take this part out, minus j theta, if I take the magnitude of this function, remember this is a complex function of theta, right? And theta is simply 2 pi f tau. So if I keep tau constant, right, and if I plot against f, right, and this is theta, if I keep tau constant, when I increase f, theta increases. So this is a linear phase relationship. So because of that, we call this a linear phase. But something very important to remember, when you delay a signal, there's a negative sign in front. So we call it a negative linear phase. So when you delay a signal, you get a negative linear phase relationship in the frequency domain. Very, very important. If you bring forward the signal in time, which you cannot do, by the way, in practice, but if you did, you will get a positive phase relationship. But in practice, you can only delay things. You cannot go back in time. You can only go in the future direction, right? So if you delay something, you are going to have a negative phase rotation given by 2 pi f tau. It has two components: the constant tau, which is your delay, and frequency variable f, that is your independent frequency. So you have a frequency dependent phase rotation that is set by the delay tau. Okay. So if I take this delay function and if I plot its magnitude, right, We know that this is from the Euler theorem, from the Euler identity. We can write this function as cos minus theta minus j theta, which is equal to cos theta minus sin. So magnitude of e to the minus j theta is equal to square root of cos square theta plus sin square theta, which is equal to 1. The phase rotation doesn't change the size of the x of f. Its magnitude is always 1, but its angle, right, theta is equal to tan inverse no, I can write this as this. So it's by definition sin theta divided by cos theta, right?
Is that Q or theta?
Sorry, what?
Is it Q or is it theta?
There's Q. There's no Q.
Oh, so the minus J is theta. Okay.
Theta, theta. So this is theta. Plus or minus. The minus is inherent. So let's do a problem. So we are going to do a small problem. Let x1 of f is defined as the Fourier transform, x0 of f, Fourier transform of x0 of t. Use the properties scaling or linearity and delays to write down an expression for the Fourier transform of x1 of t in terms of capital X0 of where capital X0 of f, yeah, 0 of t is a Fourier transform pair between so it looks a little cryptic, but it's actually very simple. So all we are saying is we have a function x0 of t in time, right? And that's got its Fourier transform capital X0 of f. Now I'm defining a new function x of t, x1 of t, which I haven't written down yet. x1 of t is defined as some linear scaling and addition of the original function x0 of t. So given that, can you find the Fourier transform of the second one using capital X of 0 of f? So let's say simple y, my apologies, x1 of t, I'm going to define as half times x0 of t minus 1/3 times f0 t minus. So the question is, find capital X1 of f. So take a moment for that to sink in. We have x0 of t, the Fourier transform capital X0 of f, right? I'm calling x1 of t as half times x0 of t minus 1/3 times x0 t minus 10. So I'm scaling and I'm delaying and I'm adding. So given we know how Fourier transforms behave, can we put together these two sections, right, to get the answer? So we will first do it in two ways. We will first do it manually, right, and then we will use the properties to see how we can actually accelerate computing of Fourier transforms using the properties. So take a note of this, because I only have one board. I do have to erase it. Give you a moment. Take note of it. Everything's on the WhatsApp, right? So I'm going to leave this part out so that I can see what I wrote. So manually, I would start by applying the Fourier transform. I would say x1 of f is defined as integral x1 of t minus j 2 pi ft dt. That's by definition, right? I just plugged into the definition of what a Fourier transform is. Now I have to plug this one. So I substitute my version of x1 of t, which is defined in terms of x0 of t, into the definition of the Fourier integral, which gets me a big equation. I'm going to plug in x1 of t here, which is equal to half 0 of t minus 1/3 x0. So I can simplify. Half 0 of t e to the minus j 2 pi ft, right? dt, I'm kind of simplifying, minus integral 1/3 0 t minus tau . So this half pops out. I get half t dt. 1/3 pops out here. 1/3 j 2 pi f voice 10 t minus tau . I can simplify and do the dance and get the answer. That's the long way of doing it. But the whole point of knowing the properties is that you don't have to do all these things. That's the lesson, right? I'm just showing you one time how messy it is to do everything from scratch without exploiting the properties. Okay. So you can see that you can chug through all this math and get the answer if you want. but that's an extremely laborious way of doing things. We are not going to do that. We are just going to show you here how bad it is so that you appreciate the properties. That's all. Okay. So this is the long way of doing things. And now we'll talk about the short way of doing things. All right. Keep this one be. All right, so let's see how we can use the Fourier transform properties to solve this quickly. Now, let's say we have a function x is equal to x1 plus x2. This is simply linear addition. So if I find the Fourier transform of x of t and plug in here, right, I will get the Fourier transform x1 of t plus x2 of t so I can write the integral as two integrals, which is equal to integral of the first part plus the integral of the second. So if I call this part one Fourier transform, the Fourier transform of x1 of 1 of f, right? X1 of capital F, and the second one x2 of f, I can see immediately that when I have a function that is the summation of two component functions in time, their corresponding Fourier transforms also add. So if capital X, sorry, if simple x is the sum of simple x1 and simple x2, the Fourier transform of simple x, which is capital X, is equal to the Fourier transform of simple x1 plus the Fourier transform of simple x2 from linearity. So we can write the two components simply as x1 capital F plus x2 capital F. The property moves from time to frequency. So knowing that, it's very easy to solve the question. Let me take a quick photo. And then we'll see how we can solve the problem, right? So here, I'm going to think of this part as x1 of t and this part of x2 of t. Two component set. So if I know that the total Fourier transform is the sum of the individual Fourier transforms, I can find the Fourier transform of this part separately, find the Fourier transform of the second part separately, and add them together, right? Which is exactly what I'm going to do. So the Fourier transform of the first part I can write down by inspection x1 of f is equals x of f, let's say, in numerator x final of f is equal to x1 of f plus the first part becomes 1/2 x0 and the second part is minus 1/3 0 of f e to the minus j 2 by f. So I can write half minus 1/3 e to the minus j 2 by f times 10, the common factor, times the original Fourier transform.
I have a question. For the first function, don't you have to put a parentheses between 1 over 2x naught f minus 1 over 2x naught f? Don't you have to put a parentheses
No, because it's multiplicative, right? So you have multiplication, and subtraction. So in algebra, you first have to do the multiplication part.
What do you put in parentheses between x? I'm saying when you put a parentheses between the equal sign at 1/2 and x of x naught of f and e, you put a parentheses.
So the term is the only term that has the first term is not the second, that's right.
Oh, okay.
Yeah, so minus 10 is just tau, so this is tau, right? So tau is equal to 10 in my example. All right, so let's do a problem. So I'm going to give you the Fourier transform of a rectangular pulse, and we'll prove that equation later on. But right now, just take my word for it. So let's say we have a rectangular pulse x r of t, which is defined as a for t less than tau by 2, a greater than minus tau by 2, t less than tau by 2, and 0. Yes. So this is my standard pulse. T. Minus tau by 2, plus tau. So let's say xr of t has a Fourier transform capital X r of f. Capital X r of f is equal to a tau sinc. So this is pronounced sink, like the kitchen sink, but with a C. So what is this sinc function? The sinc of x is equal to sine of pi x divided by so we need a little bit of limits in calculus to compute the limit as x goes to 0. So you can see that sine of pi of x is a sine function scaled by pi in the variable, right? So when x goes to 0, sine of pi of x goes to 0 because sine of 0 is 0, right? But we have a bottom part, a denominator that has pi of x. So as x goes to 0, both the numerator and the denominator both tend to 0 and causes a problem because at exactly 0, x equals 0, we tend towards something like 0 divided by 0, which is not defined. But for other values, as x gets larger, the sine component is oscillatory. There's no change. It's still a sine function. And the 1 over pi x is a asymptote to 0. Right? So it scales like that to 0. So we have one function on top the numerator. The numerator is a sine function. So this is sine pi x. And the denominator 1 over pi x goes to infinity, but it goes that way. 1 over pi x. So from basic calculus that you have taken elsewhere, we know that as x tends to 0, if I take the limit of sine pi x over pi x as x tends to 0 is equal to 1. So my sinc function is similar to a sine function. So this is my x. It starts at 1 and has an oscillatory nature like that towards infinity. It's my sinc. So the 0 points are the same as sine, same as the zeros of sine. So we'll do that in a minute. If you take a rectangular pulse of duration tau that's centered on t equals 0 with height a, and you compute its Fourier transform, the spectrum or the Fourier transform of a rectangular pulse is given by a tau times sinc f tau. Okay. So here x is equal to f tau. So I can write that as a Fourier transform pair xr of t, as a Fourier transform pair capital R of f, where capital R of f is equal to a tau sinc f tau is equal to a tau sine pi f tau divided by . So the sinc terminology is just a word. What it really means is that every time you see a sinc function in your mind's eye, you have to visualize a sine pi f divided by pi f. So the pi is missing here, right? So every time you have a sinc with some quantity here, its expansion is actually sine pi times that divided by pi times this. So the pi is inherent in the sinc.
Is that a plus or a f?
There's no plus in there.
In the denominator, is it pi ft?
Yes. All right, so the question or the problem would be, we take a pulse string so we're going to take a bunch of rectangular pulses now. So the first pulse is the standard pulse. Okay, so this is my first component. So this is minus tau by 2 to plus tau by 2 is height A. Then I have a second pulse. So, and this delay is capital T, and this duration is tau prime. And this height is A prime. So I have two pulses happening one after the other. The first pulse, boom, is the standard pulse at t equals 0. It goes to 0, and then after a while, the voltage of the signal jumps to a different height, A dash. It's now occurring capital T time later, and its duration is also different. It's tau prime. Okay. So I can think of this waveform and this waveform as a superposition of two waveforms. So I can write this whole thing as the sum of something like this. Right. The first part would be just the usual thing. Okay. So this A minus tau by 2, tau by 2 is 0, right? Plus a second component, which is a delayed, scaled, and stretched version of the first pulse, right? It's delayed because it starts at this point. It's delayed by capital T, shifted by capital T. It's stretched because the duration is no longer tau, but it's tau prime, so it's a different value. And stretched this way also because the height is now A prime, not A. So I have a second pulse that goes. So this jumps. Let me use a different color. I'm going to see. Okay, let's try it. T. This T minus tau prime by 2. This is T plus 2. So imagine in time domain, the pulse sequence has a superposition of two individual rectangular pulses. So we can find the spectrum of each one separately and we can add them up, right? So the spectrum of this, let's call this waveform x1 of t and this waveform x2 of t. So my x of t is simply x1 of t plus x2 of t. So I can take the Fourier transform of this, which means I have to take the Fourier transform of the right-hand side also. X of f is equal to the first Fourier transform, capital X1 of f, plus the second Fourier transform, capital X2 of f. Two individual waveforms, individually Fourier transformed and added because in the time domain, the same operation is happening, right? So I can write down the first one is easy. It's directly capital R of f. So I will get A tau sinc f tau from here. And then from here, I will get plus. Now, what has happened? Several things have happened. It's delayed, right? The height is different and the duration is different. So we can take the height is different into account by replacing A with A prime. A prime duration is now A tau sinc f tau, and then we have the phase component. So my final answer is A tau sinc f tau plus A prime tau prime sinc prime. Just algebra. I individually found the Fourier transform of the first pulse, A tau sinc f tau, usual one. Then I individually found the second Fourier transform. Now that has a phase component because the whole thing is delayed by t. That is why we have this component. Right? Then its duration is no longer tau, it's tau prime. So everywhere we had tau, we had to replace with tau prime. Right? And its height is no longer A, but it's now A prime. So everywhere we had A, we had to replace by A prime. Then get them together. Very easy. Once you get the hang of it, it's not difficult. You have to think in your mind how to take the waveform, a complex waveform, a complicated waveform. Think of it as a superposition of multiple simple components. You find the simple components separately using the theorems, and then you add them up to make the complicated. So with that, I'll end for today, and I'll see you on Thursday.